Okay, in this video, we're going to start going over some solid-state electronics topics. So in the solid-state electronics section, we're going to be talking about some different solid-state electronics, such as diodes, which we'll be going over in this video. We'll be talking about the ideal diodes, Zener diodes, and real diodes, and how they operate in their different modes of operation. We'll be going over different types of transistors, such as MOSFETs, Chaifetz, and BJTs, and we will also be talking about Thyristors. And with all of these, we'll be talking about different ways of biasing, which we're going to be going over right now. Okay. Biasing refers to the mode of operation of a device and the designing of a circuit to operate a device in a specific way. So when we're talking about biasing different solid-state electronics, we want them to operate in a certain manner. And as you'll see later on, we'll be going over different solid-state electronics, and they have multiple modes of operation. So biasing basically refers to designing a circuit in a way that makes the electrical component operate in one of its specific modes. Alright, now we're going to be going over ideal diodes. Okay, so now we're going to start talking about diodes, specifically ideal diodes. So, what is a diode? Well, a diode is a semiconductor device that allows current to flow in one direction but restricts current flow in the opposite direction. So this is a diode, and this is how it will be drawn in circuits, where the anode, which is the positive side, and the cathode, which is the negative side, is on the left and right side of the diode. Now, when we're talking about diodes, we want to be talking about the different modes of operation. So first off, when we're talking about a diode, we have two modes of operations for an ideal diode. We have the forward bias and the reverse bias. So the forward bias of a diode essentially makes the diode act as a closed circuit. There's no resistance across the diode. But in the reverse bias, it essentially acts as an open circuit, or think of it as infinite resistance. So to operate in the reverse bias region, the voltage across the anode and the cathode has to be less than 0. And when the voltage across that is less than 0, it will have 0 current flow. And then when the voltage is greater than 0, it will have a positive current flow. Now we're going to go over a problem that involves a diode. Okay, so here is a problem, and as you can see, there is a diode here. Now, what we want to do is we want to find the current that passes through the diode. So the way that we're going to do that, the first step is we're going to assume whether the diode is on, meaning that's in forward bias, or we're going to assume that the diode is off. And then we're going to verify our assumption to make sure that we're right. And firstly, we're going to start off with, which way do you want to assume? Do you want to assume that this diode is on or off? And in this problem, it starts off kind of simple, so I can give you some intuition on how you would want to solve this. So we want for the diode to be in forward bias when there's a greater positive voltage on its anode, the positive side over here, and a smaller voltage on its cathode side. Well, we have this 10 volt voltage supply, which means that this side is going to have 10 volts. And on this side, we have a 5 volt voltage supply, which means that this side is going to be either 5 volts or less. So we can already tell that this is probably going to be in forward bias. But we're going to start off with this problem by assuming the opposite. We're going to assume that the diode is in reverse bias, which means that it's an open circuit. So now we're going to redraw the circuit so that it represents an open circuit. Okay, so now that we've redrawn the circuit with the diode in the reverse bias, meaning that it's an open circuit, we are going to assume that I is equal to 0, and we're going to verify that VD is less than 0, because these are the conditions for the reverse bias. The VD being the voltage from that point in the circuit to that point in the circuit. And to verify this, we are going to use circuit analysis to find the voltage at this point. We'll call it Vx, and then use that to find Vd. So we can already ignore this part of the circuit, because with the diode being in a reverse bias, which means that this is an open circuit, it won't have any effect on what the voltage is here. So we can just find the voltage at this point using the 5 volts voltage source, the 1 kilo ohm resistor, and the 3 kilo ohm resistor all in series. And we use KCL to find the current going out in both directions, because the sum of those have to be set equal to 0. So we will see that the equations give us Vx minus 5 divided by 1k plus Vx minus 0 divided by 3k, set equal to 0. And from this, we can see that 3Vx minus 15 plus Vx equals 0, which means that 4Vx equals 15, and we'll see that Vx equals 3.75 volts. Now, to find out what Vd is, we're going to find the voltage here, which is 10 volts, minus Vx, which is going to be 3.75 volts, which is going to leave us with Vd equal to 6.25 volts. Now, this does not verify our assumption, because Vd needs to be less than 0 and Vd is positive. So now we are going to assume that the diode is in forward bias and then analyze the circuit again. Okay, so now that the diode is in forward bias, mean that it's a closed circuit, we are now going to find the current that flows through here, because now we are assuming that the voltage across the diode is going to be equal to 0, and now we need to verify that the current through the diode is greater than 0. And to do this, we're going to use KVL. So we're going to find the current in these two loops, which will help us find our diode current. So, using KVL, we know that 10 volts minus 3k times I1 plus 3k times I2, that is equal to 0. Then minus 3k I2 plus 3k I1 minus 1k times I2 minus 5 volts equals 0. Then to simplify this, we get negative 3k I1 plus 3k I2 equals negative 10, and negative 4k I2 plus 3k I1 equals 5. And then after doing some systems of equation solving, you will get I1 is equal to 8.33 milliamps and I2 equals 5 milliamps. And so ID is equal to I1, and I1 is greater than 0. So now we have verified that our assumption is correct and the diode is in forward bias. Now we're going to be moving on to talking about Zener diodes. Okay, so now we're going to be talking about Zener diodes. A Zener diode is a device that allows current to flow in either direction under specific conditions. So the Zener diode is very similar to the regular diode. The only difference is that once the negative voltage across the Zener diode reaches the Zener voltage, which will be specified in the problems, it will act in a reverse breakdown region, essentially dissipating that Zener voltage amount of voltage and allowing current to flow in the opposite direction of from the cathode to the anode. Now we are going to do a problem based around the Zener diode. Okay, so now we're going to be looking at our first example for the Zener diode. So the problem says if the input voltage here is equal to negative 32 volts and the Zener voltage is 12 volts, meaning that there's negative 12 volts seen across from the anode to the cathode, what is the current through the diode? So the first thing we're going to do is assume whether the diode is on, off, or in reverse bias. Well, if there's a strong negative voltage right here, we can assume that the current is going to be flowing this way through it, which would put it in the forward bias. So let us go ahead and assume that the diode is in the forward bias, meaning that it is a closed circuit. So let's redraw our circuit so that it shows that the Zener diode is in forward bias. Okay, so now we've redrawn our circuit to show that the Zener diode is in the forward bias, meaning it's a closed circuit. Now we want to do some circuit analysis because we've assumed that the voltage across is equal to 0. So now we must verify that the current through the diode is greater than 0. This being the current through the diode. So we'll use some circuit analysis to figure out what the current through here is. Well, if this is a closed circuit, we know that it bypasses this entire resistor. So if it bypasses that entire resistor, then we can just examine this part of the circuit. And as you can see, it is just a voltage source in series with a resistance. So what we can do is we can divide the voltage by the resistance, and that means that the current flowing in this direction, we'll call it I1, is equal to negative 8 volts. And from seeing how we've drawn our currents, ID is going to be equal to negative I1, which means that the diode current is, I'm sorry, this is supposed to say milliamps. It is 8 milliamps, which is greater than 0, which means that we have verified our assumption for the Zener diode. So, in this video, we covered an introduction to some of the solid-state electronics. Looking forward to see what is going to be in the next videos, such as transistors and thyristors. And we also went over a couple of different types of diodes. And in the next video, we'll be talking about the ideal diode and some more problems with diodes.